Hello. In the previous lecture, we were discussing something regarding recursive sequence. Today, we are going to start with an important topic, which is the subsequence. And also, we are going to see a few more questions in the convergence of sequences. So, without wasting time, let us start. Okay. So, yesterday, we were discussing. Yesterday, we were discussing something about recursive sequences. And we did a few questions on that. Today also we are going to do a few questions on recursive sequences, convergence of sequences, and a few more topics, relevant topics. And one of the important topics that I'm going to cover today is the subsequences. Okay. So what is a subsequence? So as the name suggests, it must be some subset, or you can say some restriction to the main sequence. So indeed it is. So what is a subsequence? Subsequence is a restriction on the main sequence. So I'll write it for more formally, that let X be defined from N to R be a sequence, then a subsequence, then a subsequence is the I can write is the restriction of X to an infinite subset of N. So for example, let us say I have a sequence Xn. Now if I say I restrict this N to only even numbers, okay? So I've restricted this to only even numbers. So what will happen? So basically, again, set of even numbers is also an infinite subset of N only. So this particular X to N would be an even subsequence. Or you can say subsequences containing only even labels. So this is even subsequence of this particular sequence. This is a parent sequence. Let us say I restrict my sequence such that it only contains odd labels. So this sequence is called as the odd subsequence. It's not called as, but in general, these two are a few examples subsequences. So these are two examples of subsequences. Let us say I restrict my sequence in a manner that I only take these values, x2, x3, x5, x7, x11, x13. That is, I only take prime numbers. Okay, so this is also a subsequence. This is also a subsequence to this main sequence, that is xn. Okay. Now, there's a principle called as well-ordering principle. There's a principle called as the well-ordering principle. What does that suggest? It suggests that if S is a non-empty subset of natural number, then let S be a non-empty subset of, and in fact, this is a, let's say, infinite subset. Infinite subset of natural number, then it can be listed as n1, n2, n3 dash 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 in a manner that I can always arrange them in increasing order. This is what you call as your well ordering principle. So what does your well ordering principle says? That if S is an infinite subset of n, if S is an infinite subset of natural number, then it can always be listed as n1, n2, n3, such that n1 is less than n2 and n2 is less than n3. That is, I can always arrange it in a sort of increasing. You see, increasing in such that the terms are like each of those terms, each of the next term, you can see that is greater than the previous term. So this is what is called as your well ordering principle. Okay, this is an important theorem. So just an idea I'm giving you. Idea, you can say motivation. Okay, so again, since I have written this, and I'm writing an infinite subset n of an infinite subset S of n can be listed as n1, n2, n3 in this fashion. Okay, so see how to do. What I'll do, since I know this is an infinite subset, okay, since it is an infinite subset, so if I withdraw a few elements, or if I keep withdrawing some elements, it will still remain a non-empty subset. See how? So let us say that in this particular listing, let's say I'm listing n1, n2, n3. I'm listing the elements of S. These are your elements of S. And let us assume that okay, so let us assume that n1 with the least element of S. Let S1 be the least element of S. And what I'm going to do, I'm going to take this n1 away from this S. So I'll take a set where I have taken out this n1. Okay. Now this will contain n2, n3, so on and so forth. And I'm claiming that n2 be the least element of this. N2 be the least element of S oblique n1. Oblique means S apart from n. Okay. So clearly you can see that when I had taken n1 out, then n1 was the least element. Now, if it is this particular place is taken by n2, now in the next time you can see that n2 is the least element. It implies what? It implies n1 should be less than n2, because if n2 was greater than if n2 was less than n1, then n2 would have been the least element. But n1 is the least element. I have taken the least element out. Now there would be some other element which would be least. Let's say this is n2. And let's say n2 be the least element of S oblique n1, means S subtracted n1. So basically I have taken n1 outside. Now in this set, let us say that n2 is the least element. So clearly n1 would be less than n2. And in this fashion, we'll keep removing all these elements till nk. So let us say that in totality n1, n2, n3, nk belongs to S. Now let us define a set sk, which is equals to what? Which is S except all these elements. n1, n2, n3, dash, 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 nk. It is quite easy to see that this sk would be a non-empty set. Why non-empty set? Because this is an infinite set. This is an infinite set. So it is easy to see that this would be a non-empty set. Now, in this particular sk, since it is a non-empty set, again you can choose a minimum, let us say nk plus 1. So recursively, you can see that n1 would be less than n2, n3, dash, 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 less than nk, and less than nk plus 1. So you can see that one of the most important observation you can see that if I'm choosing all those things, so let's say in any set, let's say if I had a set of natural number itself, so if I'm taking the subset to be the natural number itself, so if I'm making different subset of a set, like one of the set would be the set itself. So in any case, remember, b whatsoever, b whatsoever be the subset, let's say any subset of n, let's say S is any subset of n. And if I'm claiming that n1 is the least element, in any case, this n1 should be either equal to 1 or should be greater than equal to. Understand my point? Let's say S is any subset. Now, understand that the least element in natural number is 1. So the first element, when we chose to take out, so that n1 should be in any case greater than equal to. Either it would be 1 or it would be greater than. Let's say if I'm choosing S to be the set 2, 4, 6, 8, so on and so forth. So now here the least element is what? 2. So in any case, B whatsoever, you can say that n1 is greater than 1. Okay. Now, if I remove this 1 outside, if this is the set, let's say this, the proper, let's say that the S is completely n. In that particular scenario, the least element would be 2. But otherwise, just think of any other set. Let's say any other set. I have removed the least element. I have removed the least element. So in any case, understand that this least element should be either greater than or equal to 1. Okay. Now, let's say if S is completely n, then you can see that n2 is equal to 2. But had this not been the case, you can see, let's say I've removed 2 here. This is the least element. So this would be your n1. Now n2 would be equals to what? 4. In any case, understand your n2 would be greater than equal to 2. So understand that inductively, or one of the assumptions, that one of the most significant handy results that come out from here is that nk is greater than equal to k. Nk is greater than equal to k. This is one of the most important result. Okay, so always remember the derivation goes long, the proof is very long, but understand, I'm reiterating once again. See, just understand what I'm trying to make a point, what I'm trying to prove to you is that if S is any subset of n, then the elements of S can always be arranged in increasing order. This is the first thing that I'm claiming. How come? So let's say, just understand, let's say S is equal to n. Just for example, I'm giving. Now, if this is the subset, I mean, the subset itself, the set itself is, you can understand now, if I'm saying that what are the subsets of these. So one of the subset would be this set itself. So I'm just trying to explain from, let us take complete n. So if I take complete n, this is 1, 2, 3, dash, dash, dash. Okay. Now the least element would be 1. So I take this 1 out. Okay. Now S except n1, which is n1 is equal to what? 1. The least element would be equal to what? 2. Okay. Now the least element would be 2. Take this 2 out. The least element would be what? 3. And when I'm taking all these elements out, so I'm picking out the least element. So you can clearly see that if 1 was the least element, at first 1 was the least element, then obviously the next element which is coming would be greater than 1. Because had it been less than 1, then this would have been the least in the first iteration itself. So remember, I'm taking out, and this is how you can arrange. Let us say instead of this, I have this. So always remember that any subset S of any infinite subset S of n can always be arranged in increasing order. This is called as the well ordering principle. Okay, and how it is done? We understand that this is an infinite set, so it is not going to exhaust. It's not going to exhaust means what? Let's say at the first run, it has some terms like n1, n2, n3, just labels. It's not necessary that this is 1 only. I'm just labeling n1 as 1, n2 as the second element, n3 third, fourth. Okay, now let us say let's say n1 is the least element. So let's say n1 is the least element. So I'm writing n1 here. Okay. Now what I'm going to do in the first run, I'm going to remove this n1. So s1 is equal to what? S except n. Now let us say n2 is the least element because this set is an infinite set. So it is never going to get exhausted. This is also proven very theoretically, but right now I'm not proving it. We'll do it when we are going to take a course on proof writing. Right now, just understand this would be the least element, right? If this is the least element, then n1 would be less than n2 because if n1 was lesser than n2, n2 was lesser than n1, then n2 would have been the least element. If n2 would have been the least element in the very first iteration, n2 would have come out. So n2 is the least element. Now further I'll remove this n2. So again there would be some least element, let's say n3, or n3 means it's not necessary that this is 3. This is n3 means one of the natural. So now understand n3 will be in any case greater than n2 and greater than n2, because if n3 was lesser than both of them, it would have been plugged out in before. So now this. So this way you can, and you also know that this is an infinite subset of n. It is not going to get exhausted. This is also proven. Don't worry. I'm just trying to write one. I'm just trying to write the motivation. I'm not writing the proof, right? Okay. So in any case, understand that by well ordering principle, we know that any subset, any infinite subset of n can be arranged in this fashion. This is one. Another observation that we got was, if I was picking out the first least element, I understand that the least number in natural number is 1. So in any case, this would be greater than equal to. Now, if I take this 1 out, now the least element that remains is 2. Okay, so either 2 would be, if 2 is contained in that subset, the 2 would be taken out. If 2 is not contained, but understand this n2 would be greater than equal to. By observation, you can always write that nk is greater than equal to k. This is one of the most handy observation that you should keep in mind. This is the most handy observation that you have to keep in mind. Okay. See, again, if you are not getting it, again, I'm proving it. So let's say if S is a non-empty subset, non-empty infinite subset of n, then the least element n1 for this set should be either greater than or equal to 1. Because you understand, for natural number, the least number is 1. So n1 should be greater than or equal to 1. If I remove this n1, the next element would be, let's say, n2. In any case, understand n2 would be greater than n1, and n1 is greater than or equal to 1. So in any case, n2 is greater than 1. And what is the next natural number? So I can write n2 is greater than or equal to 2. In any case, you can write by induction that nk is greater than or equal to k. This is an important, very, very important result that you should keep in mind. Now understand, one of the most important result here, I'm trying to put it in this fashion, that if xn converges to x, that is, if the sequence converges to x, and if xnk is a subsequence, xnk is a subsequence, then these subsequences also converge towards x1. If the parent sequence is converging towards x, then the subsequence also converges towards x as k tends to infinity. So I understand that xn converges to x means what? If xn is converging towards x means what? xn minus x the mod can be made less than epsilon for all. Let us say I'm writing xk minus x ka mod can be made less than epsilon for all k greater than equals to capital N. Okay, I already know that what would be the subsequence. Subsequence contains these labels, which are nothing but the restriction to this set restriction to the set of natural numbers. So after all, this nk is element of the subset of n. Okay, so this nk would any case would be greater than k, and this k is greater than equal to n. So if k is greater than equal to n, then nk would also be greater than equals to n. It implies what? If I write this x nk minus x, its modulus will also be less than epsilon. Because see, if k is greater than n, then nk is also greater than n. For all k greater than equal to n. It implies what? It implies that x nk also converges towards x. Just a little bit of, not even proof, this is just a sketch of it. One more important result that you should keep in mind is this, that given any real sequence, given any real sequence xn, there always exists a monotone subsequence. It is an important concept. I'm not going to derive it right now. Okay, so any real sequence will always contain a monotone subsequence. All these results we are going to derive in a special series that I'm going to start. That would be real analysis and proof writing. Okay, right now I'm just considering real analysis through, I'm teaching you real analysis through problem solving approach. Okay, so given any real sequence xn, there always exists a monotone subsequence. So if there is any sequence xn, it always contains a monotone subsequence. Okay, now let us try to do one more thing. It is called as Bolzano-Weierstrass theorem. And what does it suggest? Let us write that. That if xn is a bounded real sequence, it has a convergent subsequence. Why? See, if xn is any sequence, then it always would contain a monotone subsequence. This is clear? Monotone subsequence. And if it contains monotone subsequence, further also I know that xn is bounded. If xn is bounded, then the subsequence would be bounded, and subsequence already is monotone. Implies what? That monotone subsequence plus bounded, it implies that if xn is bounded, then it will always have a convergent subsequence. Again, understand. One of the theorems says that xn, if there is a sequence xn, then there always exists a monotone subsequence for this xn. Now, given that this is xn is a real sequence, it contains a monotone subsequence. If I'm saying that this xn is bounded, if xn is bounded implies what? The subsequence would be bounded. If subsequence is bounded implies what? Already it has been given that any sequence xn will always have a monotone subsequence. If I'm saying that xn is bounded, implies subsequence is bounded, subsequence is monotone, plus bounded implies subsequence is convergent. So always remember that if xn is any real sequence and you find that it is bounded, then it will always have a convergent subsequences. Will the sequence sin n contain a convergent subsequence? Yes. Why? Because sin n is bounded. If sin n is bounded, the sequence is bounded. Any sequence, any real sequence always contains a monotone subsequence. Already I'm saying that sin n is bounded, so therefore it will contain a monotone subsequence. Okay. Now there is yet another important result. If a sequence is convergent, then all its subsequences converge to the same limit as that of main sequence. So if, let's say, if a sequence xn is convergent, then all its subsequences converge to the same limit as that of xn. So if you find that there are two subsequences to a sequence and both of them are going towards different limit, then xn can never be convergent. Then xn can never be convergent. Example, xn equals to minus 1 raised to power n. So it has two subsequences, x2n would converge towards 1, x2n plus 1 would converge toward minus 1. Clearly, xn is a divergent sequence. In fact, a few would say oscillating sequence, that is also fine, but I would use mostly divergent and non-divergent. Oscillations we'll do later on, but right now I'm saying xn is a divergent sequence. Why? Because two subsequences are there, both of them are converging to different limits. Okay, so these were some important results that I have stated for your what you can say subsequences. Okay, one important result is that if complementary subsequences, if complementary means what? If I can write, let's say if both odd and even subsequences of a sequence are converging to the same limit, then sequence is convergent and it also converges to L. Let's say the same limit I'm telling L. This is one again important sort of result. We'll prove it later on. So if in a sequence, if you're not able to find monotonicity, and if at all you're able to conclude that the odd subsequence and even subsequence, both of them are converging to the same limit, then the sequence is convergent and it also converges to the same limit L. This is one of the most important sort of important theorem, or you can say result. Let us do a question that was asked in GATE exam. Let us do a question that was asked in GATE exam. Okay, and this is an important question, and you'll learn a lot from this question. So kindly pay great attention to this question. So question says that given a recursive sequence, so in GATE it was a little bit easy. I'm making it more general. So I'm making it more general. So given a recursive sequence such that a1 lies between 0 and 1 and an plus 1 is equals to cos of an for all n belongs to natural. is an a convergent sequence? Now, in this sequence, you clearly know that this is cos, and cos in general will not let an be a monotone subsequence, a monotone sequence. Sorry, monotone sequence. Again, I'm repeating. See, an plus 1 is equals to cos of an. If an plus 1 is equal to cos of an, remember that cos is an, you can say, it oscillates. Since it oscillates, it is not going to let an be a monotone sequence. Okay, so it is very difficult for you to understand how to approach this particular problem. So the best way in such a case where you're not able to prove, see, what was your general approach? Either you find limit, or at times when you are not getting any clue from the question, what you do, you basically try to prove that your an is a bounded sequence and you prove that an is monotone. But here you know that your an plus 1, that is an also you can say, because an would be equals to cos of an minus 1. Understand this an is equals to cos of an. Now cos is an oscillatory function. And since cos is an oscillatory function, it will not let an be a monotone sequence. So what is the good way? The good way is to use the subsequences. Use of subsequences. Okay, how would we do? Just let us first try to draw the graph of something. So basically what is happening, if at all this limit exists, let's say we think that if it was a convergent if an was a convergent sequence, then an would converge to L, and then L would be equals to cos of L. So the first thing that comes to mind is, let us try to see whether L is equal to cos of L or not. So basically this is how you draw the plot of cos. And if I make the graph of simply x, this will be it. So this is x, this is your cos of x. And let us say this is your point x naught, which is the unique root of cos x is equal to x. Now, one thing is quite clear, that a1 lies between 0 and 1. What is 0 and 1? So clearly I know in the first quadrant, the angle goes from 0 to pi by 2. So basically a1 means what? It lies between 0 and pi by 2. That is a1 if I'm using it as an angle here. So this angle lies in the first quadrant. So your a2 also would lie between 0 and 1, because in the first quadrant cos is positive. And when cos is positive, it lies between 0 and 1. So in general, I can write that my an would be lying between 0 and 1, implies an as a sequence is a bounded sequence. Now see, we understand that, I'm writing it here. We understand that cos x, या फिर or cos x is an oscillatory function, or you can say it is a periodic function. So it will not, so an plus 1 is equal to cos of an will not be monotone. Monotone means what? Either increasing or decreasing. But cos of s decreases, then increases. So it cannot be monotone, clearly. So we'll keep an eye over odd subsequences and even subsequences. So idea is that we'll keep an eye at odd subsequences and even subsequences. Okay, and x naught, please do remember, x naught is a unique root of cos x equal to x. So just keep an eye on all these things, and let us start with the question. So what would be your a1? A1 is nothing, but what would be your a2? A2 is simply I think A1 was given to you. A2 is cos of A1. And what is A3? A3 will be cos of A2, which is cos of A1. And as I already told you, that since the terms are not monotone, so there is no point comparing an plus 1 and an. Rather, we should shift our attention towards the subsequences. So I'm going to compare A3 and A1. I'm going to compare A3 and A1. Comparing A3 and A1 means what? Comparing A1 and cos of A1. So this is A3. So comparing A3 and A1 means comparing cos of A1 and A1. So what do you think the function should be? So let us take let us try to construct a basic, you can say, framework. This is your cos x is equal to x. Again, I'm redrawing. This is your point x0. Now, without loss of generality, you can also take another case also. I'm taking one of the cases. Let us say that x is greater than x0. Let's say x is greater than x0. Okay. Let's say x is greater than x0. Sorry, x is greater than x0. Just think x is greater than x0. So if x is greater than x0, so let's say here it is. We are here. Here you can see that this is bigger and this is less. This is bigger and this is less. So I can write for all x greater than x0, for all x greater than x0, for all x greater than x0, clearly x would be less than cos of x. And if I take cos of, okay, so we have to compare cos of x. So it's better to, so leave this idea, sorry. So basically what we need to do, we need to compare odd subsequences and we need to compare the terms of odd subsequences and even subsequences. So we need to compare A3 and A1, or probably A5 and A3, and so on and so forth. And what is A3? A3 is cos of A1. So we need to construct a function f of x, which is equals to cos of x minus x. Okay. Now, another thing is that we don't know the location of A1. We don't know the location of A1. Where is A1? It is clear that A1 lies between 0 and 1. It implies it lies in the first quadrant. First quadrant means what? It lies between 0 and pi by 2. That is the first quadrant. So basically, it lies somewhere from here to here. So let us say, without loss of generality, you can also assume the contrary. It's up to you. I'm assuming that A1 is greater than x0. Let us say that A1 is greater than x0. After all, x0 also lies in the first quadrant, and A1 also lies in the first quadrant. We don't know whether A1 is greater than x0 or A1 is less than x0. In fact, we don't know anything about A1. We have given hint that A1 lies between 0 and 1. So without loss of generality, I have written that A1 is greater than x0. Just, you can take otherwise also. It's up to you. Now let us first take the one of the cases. The other case you can do at your home as a homework, right? As a homework. Right now I'm trying to do this case. Now, in order to compare A3 and A1, we have to compare what? We have to compare cos of A1 and A1. So basically, the structure that goes beneath is cos of x minus of x. Now let us try to explore a little bit about this function. So this function, if I differentiate, what I'll get? I'll simply get derivative. Derivative would be equals to minus of sine of cosine x, again minus of sine x, again minus. And we know that if x lies between 0 and 1, and remember, this I'm proving for all x lying between 0 and 1. Why? Because we are interested here only. Why? Because after all, instead of x, I'm going to place A3, A1, and I know that all these things, A3, A1, and all these things, AN, lie between 0 and 1. So basically, I have constructed a function in order to make some judgment between A3 and A, or probably A5 and A3. Okay, so understand that f dash x is equal to what? Sine, cosine, sine. This lies between 0 and 1. This also lies between 0 and 1. minus 1. So clearly f dash x is less than 0 for all x lying between 0 and 1. I can say that my f of x is a decreasing function. Okay, we have already assumed that a1 is greater than x naught. I have already assumed that a1 is greater than x naught. A1 is greater than x naught. F is a decreasing function. That implies f of a1 would be less than f of x naught. And remember what is x naught? X naught is that point where your cos of x naught is equal to x naught. So now here, what would be your f of a1? F of a1 would be cos a1 minus of a1 less than. What is f of x naught? This is cos of x naught minus x naught. Remember, x naught is that point where cos of x naught is equal to x naught. So this will become x naught. If this becomes x naught, what is cos of x naught? Cos of x naught is again x naught. So this becomes overall 0. So I can clearly write that cos of a1 would be less than a1, which implies what? Which implies that a3 would be less than a1. A3 would be less than a1. Similarly, just think about a5. Just think about a5. What can you think? A5 would be greater than a3 or not? So if you find that what would be a5? A5 would be cos of a3. Just see. What would be your a4? A4 would be, I think, a4 would be cos of a3. And what would be a5? A5 would be cos of a4, which is cos of a3. So in order to compare a5 and a3, we have to compare a3 and cos of a3. So basically, if I'm trying to compare a5 and a3, actually I'm comparing cos of a3 and a3. I think it is clear. Okay. Now, in order to compare this, how should I go? I know that, so I'll write it here. Let us take another function. Let's say g of x. G of x is cos of x, not cos of x minus x is f of x. I'm again considering another function, cos of x for all x lying between 0 and 1, and try to differentiate it. If I differentiate it, what I'll get? I'll get minus sine cosine of x and again minus of sine of x. So overall, I know this is positive. So gx is an increasing function. Now, I want to compare a5 and cos of a3, which is equivalent to comparing a3 and cos of a3. Okay. Now I already know that a3 is less than a1. Apply this g on both sides. So g of a3 would be less than g of a1. Why? Because now g is an increasing function. It is not decreasing. Had it been a decreasing, then inequality would have been reversed. And what is g of a3? It is cos of a3. And what is g of a1? It is cos of a1. What is cos of a1? It is a3, and cos of a3 is what? A5. So one thing is quite evident, that the odd subsequences are following this kind of trend. Which implies that this particular odd subsequences, this particular odd subsequence, you can see from here, it is the odd subsequence of what? It is odd subsequence of an plus 1 is equals to cos of a. Just see it here. Okay. Now, so a2n minus 1 is a monotonically decreasing sequence. Monotonically decreasing sequence. Okay, this is one. Now think about what would be odd subsequence like. How would odd subsequence behave? So we already know that your a2 is equals to what? It is equals to cos of a1. And I already know that a1 is less than x naught. Oh, sorry, a1 is greater than x naught. Sorry. I think a1 is greater than x. Sorry, a1 is greater than x naught. So I'm writing it here. A1 is greater than x naught. Since a1 is greater than x naught, if I apply on both sides cos, so cos of a1 would be less than cos of x naught, because cos is a decreasing function in the first quadrant. Cos is a decreasing function in the first quadrant. So clearly a2 will be less than x naught. So a1 is greater than x naught, but a2 is less than x naught. A2 is greater than x naught. So this, let's say this is your x naught. So your A2 would lie somewhere greater than x naught, and A1 would lie, sorry, A1 would lie greater than x naught somewhere here, and A2 would lie somewhere here, less than x naught. This is quite evident. Now we know that your f of x is equal to what? Your f of x is equal to cos of x minus of x, and this is a decreasing function. Apply on both sides. So your f of a2 would be greater than f of x naught. Why greater than f of x naught? Because understand f is a decreasing function. If I apply it on the argument where a2 is less than x naught, so f of a2 will become greater than f of x naught. And what is f of a2? F of a2 would be cos of a2 minus of a2 greater than 0. Remember, f of x naught we also we have written for previously also. F of x naught means what? It is cos of x naught minus x naught, which is equals to cos of x naught minus x naught. And x naught is that point where cos of x is equal to x. So basically, this would go to 0. Cos of a2 is a4, so a4 would be greater than a2. And since a4 is greater than a2, apply g. So g of a4 would be greater than g of a2. Remember what is g? G is cos of x. So this is cos a4, and this would be cos a2. Cos a4 would be a6, and cos a2 would be equals to a4. So clearly you can see that your a2n, it behaves in a way that it is an increasing sequence. So even subsequence is increasing, and your odd subsequence is monotonically decreasing. So I'm writing it here. Your even subsequence is monotonically increasing, and the odd subsequence is monotonically decreasing. Remember that your an is bounded. So it implies this is also convergent, this is also convergent. After all, a2n minus 1 and a2n are subsequences of an. If the parent sequence is convergent, then the subsequences are also convergent. If the parent sequence is bounded, then the subsequences are also bounded. We've already proven that these subsequences are monotone, implies both odd and even subsequences are convergent. And if I prove that these two odd and even subsequences converge to the same limit, then the sequence is convergent. This result I have written. I will prove it anytime later on. I have written this statement here. So if both the subsequences, that is odd and even, converge to the same limit L, then the sequence also converges to the same limit. And therefore, we can also prove that the sequence is convergent. So here the sequence was proven bounded, but it cannot be proven monotone. Why? Because an plus 1 equal to cos of n. So what route did we take? We started with applying some functions, and we have proven what? That order subsequence is decreasing, even subsequence is increasing. Further, since the sequence is bounded, so therefore these odd and even both subsequences would be bounded, implies both odd and even subsequences are convergent. And now let us say this order subsequence a2n minus 1 converges towards L1, and let's say even subsequence converges towards L2. It implies what? An plus 1 is equal to cos of an, and it implies what? L1 is equal to cos of L2. So if I take n to be, let's say, even, then n plus 1 would be odd. And if I take the limiting case, both sides, so L1 is equal to L cos of L2, or I can write that L2 is equal to cos of L2. When do you think that this L1 and L2 becomes equal? There is only one point. If I take L1 is equal to L2 is equal to x naught, if I take L1 is equal to L2 is equal to x naught, then clearly this will become what? L2, if L2 is x naught, so this will become x naught. What is cos of x naught? Cos of x naught is x naught, and L1 will become x naught. So if I take L2 is equal to x naught, what I'll get? L1 equal to x naught. If I take L1 is equal to x naught, cos of x naught, remember x naught is what? X naught is that point where your cos of x is equal to x. So if I take L2 is equal to x naught, I will get L1 also equal to x naught. If I take L1 equal to x naught, I'll get L2 equal to x naught. It implies if both subsequences converge to x naught, then the sequence is convergent. And remember, there is only one such point. So this is a unique point. So therefore, the limit is unique. So I can say that, yes, indeed, there is a solution to this. The only solution to this is what? That both L1 is equal to L2 is equal to x naught. So if both the odd and even subsequences are converging to the same limit, then it implies that an is convergent, and it also converges towards what? The same limit, which is x naught, which is the unique root of cos x equal to x. So I hope I've been able to give you a little bit glimpse of how to use subsequences. Okay, we'll do a few more questions tomorrow, and then we will try to revise our real analysis via some questions. We'll also try to revisit how to find limits, and then I will take a little bit of a sessions on proof writing along with questions. So this is what my plan is. I hope to meet you tomorrow. Till then, take care. Bye-bye.